And here we are once again at the physics video lecture. It is Psci 168, video lecture 26. Let's begin. I have here the exam solutions. I'm going to begin just by writing up a few numbers and discussion of the recent exam. And the first two problems, force and shape and size of Earth, I gave quite a bit of information on that in the prior to the exam review. So there were no particular numbers in there. You wanted a labeled sketch and calculation of everything. So I'm just going to check those. So what I will say is you want to present those at length and not too briefly. Okay. So this one was force, etc. This one was shape and size of Earth. Actually, for the shape and size of Earth, I should point out, you wanted to talk about how we know the shape, maybe talking about the phases of the moon, and then go to the construction of the size of the Earth. Okay. But yeah, that's all review stuff from that you would have in your notes. Third one, the satellite orbits. So this one, satellites, near-Earth satellites that we've been studying, you can talk about how it doesn't need or needs to have a frictionless environment, so there has to be no atmosphere. Law of free fall, so I'll just put here no friction. Free fall, h is 1/2 g t squared. The horizontal throw is an element. And having done that, you can then do this construction here, this geometric construction, R, L, R, and this little bit here, H. H is much, much less than R. Pythagorean theorem. And then you find that V, or L, is equal to the root of 2RH. Now what I changed was to use some data from Mars. So what we had was radius of Mars and the G on Mars as well. So I gave you those, and then you took this H here is 1/2 G of Mars times 1 second squared. Okay. So you put all those numbers in, and then V was equal to L over T. So L is what we calculated here, T was 1 second, and we end up with 3,547 meters per second. Okay. So yeah, if you want to go back and calculate that, everything that we had to do is in our review notes. And we've actually done it many times, but we never used the radius of Mars, and we never used G on Mars. Otherwise, it was the same calculation. Okay, so that's interesting. What else do we have? Then for problem 4, we have the potential energy of the water in that dam. If you multiplied in that reservoir, you multiplied all those numbers together, you obtain 1.323 times 10 to the 14 joules. Times 10 to the 14 joules when you multiply that all together. I use G as 9.8 meters per second squared. And you do the conversion, you get 3.675 times 10 to the 7 kilowatt hours. At this point, you can compare this number to how many kilowatt hours you pay for every year in your own household, and then you'd know how many households could be supplied by that dam. Okay, so that's a useful knowledge. Useful knowledge. Good. If you use G equals 10, which I don't really mind you doing, then the numbers are going to be slightly different than this, okay? Off by a couple percent. So no big deal. And finally, for our Niagara Falls problem, yeah, let me say something, because there are a couple of characteristic mistakes being made here. This power mass MGH over time, right? When we put the parentheses around M over T, we don't do any division here. I gave you M over T. I don't introduce a new symbol. So the mass per time, the flow rate, I just leave it as that, and I gave you a number for it, multiplied by 9.8, multiplied by H, which was I think 50 meters or something like that, 55 meters. And you get 7.5 times 10 to the 7 watts. 10 to the 7 watts. Good. So that's what I'll say about it right now. If you have more questions, just let me know in the email and we can return to any of these. Final's cumulative, so any of this could show up on the final again as well. Okay. So now we're in a section on thermal physics where I'm trying to get to the heat engine, but I have one more really important theoretical concept. So let's go ahead and talk about thermal physics some more. All right, we've done an enormous amount in thermal physics now, and we've made contact with energy, right? But we have temperature, we have energy, we have a lot of things, and a lot of phenomena. What I want to talk about today is something called entropy, and that is something that relates to order and disorder. And as I introduce this and discuss it, I'll be bringing in the thermal physics concepts that we've had already. Okay, so order and disorder. Okay, underline it with a color. So let's just start with a system, or let's start with a block of ice. So this is ice, and we know that if we add, I have another color here, if we add heat to that block of ice, it will melt. So now we have the water in the liquid form, and if we add some more heat, more thermal energy, got to draw that balloon, right? We'll have, there's a balloon. So we have what? Solid, liquid, and gas. We could also say we have more order here because all of the water molecules are locked into place. They're orderly. After we add energy and melt the water into liquid water, they're less orderly. They can move with respect to each other, and they do. Okay, they're not just frozen into place. And we keep adding heat, we turn it into a gas, then there's even less order. Or we could say there's more disorder. So this entropy word here, it's a concept where we need a measure of the disorder. Okay, so entropy, a measure of disorder. And yeah, this was our adding energy, and so we could say the entropy is increasing from ordered to disordered. And then if we go in the other direction, as we've talked about as well, then the entropy would be decreasing, and it's going from disordered to ordered to even more ordered, okay? So entropy is a measure of the disorder, increasing entropy, increasing disorder. And there are many, many examples of this. If you dissolve a spoonful of salt in some water, then before you did put the salt in the water, you had a spoonful of salt, you had some water, that's comparatively orderly. You dissolve the salt, it's now disorderly. You have more entropy because it's been dissolved. Okay. But we're not doing chemistry here, so we're just more interested in the energy aspect of the order and disorder. Okay. So entropy is a measure of the disorder. So up here, entropy is increasing. Increases. And down here, the entropy is decreasing. So yeah, it's nice we can put it in the context of our states of matter and decreasing. Okay. So there's the entropy. The next example is going to be the heat transfer by conduction. Because I have a nice picture of that. Remember, we've got our candle, and it is heating the aluminum rod, and as the energy flows in this direction, how does the energy flow? It's because the molecular collisions, where the molecules are agitated, they collide, and therefore the agitation is moving in this direction. So you could say that there's disorder, and the disorder is spreading here. So when the whole thing is heated up, it's more disordered. So the flow of entropy, again, is along, not the flow, but the change of entropy goes along with the flow of heat, with the direction of the flow of heat. So if we're talking about heat transfer, remember we have this cartoon, and we've got TH, TC, and we know that the energy always flows spontaneously from the higher to the lower temperature. Okay. So good, that's the idea of entropy, a measure of the disorder that we have in our thermal systems. Okay. Now there is an actual formula that I'm going to introduce, because we're going to use it. For our purposes in this class, it would actually be enough to know this, but the formula is going to be used later on in a really crucial way. So let me give you a mathematical expression and show that it makes some sense. This is getting pretty technical, but can't restrain myself here. It has to be done. So change of entropy. I should be numbering these things, right? That was 1. This was 2. This was 3. Okay. Okay, so change of entropy. We have the examples up above. Change of entropy. The formula is this, and I'll get the formula and the rules for it. The delta S is equal to Q over T. Okay. Q over T. I could call this a delta Q. Let's call it a delta Q over T. And so what is delta Q? That's the energy that enters or leaves a system. And T is the temperature of the system in Kelvin. Okay. So delta Q is equal to the thermal energy, which is the heat that enters or leaves a system, and T equals T in Kelvin. Very important. So that's the change of the entropy in a system. So for example, we're just going to use this picture a couple of times. So if Q enters this object here at temperature T, then change of entropy is this many joules divided by this many Kelvin. Okay. Delta S units joules per Kelvin. Okay. Energy enters. Now the convention we need here, if delta Q greater than 0 or entering something, then delta S is greater than 0. And if delta Q is less than 0, if the energy leaves, then the entropy is negative. Okay. So that, did I write that? I said that already, yeah. Well, I mentioned it here, right? Energy entering or energy leaving, and entropy increasing or decreasing. If delta Q less than 0, then delta S less than 0. In a sense, it's always in this definition here, but we got to be careful about the delta Q. Sometimes I just take magnitudes. Okay, but T is always a positive number. T is always a positive number. Okay. So what I'm going to do now is 5. Next, an isolated system. This is really important. So we have an isolated system, and our way of thinking about an isolated system, we're just going to take this thing here and put it in an ice chest and close the lid. Okay, that's the idea that there's no heat going in or going out. It's just whatever's inside. And that will get us where we want to go. Okay. So what we're going to do is just take this concept here that I have on the board, and essentially this definition, and apply it to this picture here, which I'm going to redraw. And the thing about that cartoon is we're just saying energy flows from hot to cold. Okay, something that nobody, hopefully, is going to argue with. So here's our isolated system, and here's what's happening. We take a hot object and a cooler object, and when I say they're isolated, we just put them in a box where there's no energy flowing in, no energy flowing out. That's why we say it's a cooler, okay? And we know that thermal energy goes from the hotter to the colder, okay? So what we're going to do is consider the total entropy change. Delta, I'll write it out in words and then I'll, so consider the total entropy change. Because it's isolated, delta S total is going to be the delta S, I'll write sub H, plus the delta S sub C for the one side and the other, okay? And the delta S sub H here is the energy is leaving, so it's minus Q, I'll put an absolute value of the Q there, okay? Energy is leaving, the delta Q is negative over T sub H. And that self-same energy is going into the lower temperature object, so that's plus that same Q divided by T sub C. So let's simplify this. That's equal to common factor Q, which is a positive number. Okay. And then what will we have? We'll have T, we'll have 1 over TC minus 1 over TH. Just to make sure we simplify that some more, that will be Q, and then we get a common denominator, and we'll have TH minus TC over TC times TH. Okay. Now this is the punchline. So let me go ahead and rewrite this, or I'll put a box around it. Delta S total is equal to Q T H minus TC TC TH. Okay, so what's the point? What is the point here? The point is this. This is always positive, right? Hotter minus colder, that's a positive number. Everything here is positive. So this delta S total increased. It increased when you just let two things experience heat transfer, okay? Delta S total increased, and it turns out this is a law of nature, okay? If you have an isolated system, and that's our idea here, if you have an isolated system, you put things in it and just let it alone, the natural process will correspond to an increase in entropy, total entropy, and in particular, increase in entropy and heat flowing from, we have the picture here, heat flowing from hot to cold, and increase in entropy can be identified with each other, okay? So that's a natural law. It's called the second law of thermodynamics, and we're going to make use of it later. That's why I'm bringing it up so in this depth. Okay. The point being that delta S disorder increasing is the same as energy flowing from hot to cold. So let me check the clock. We're pretty much going to end with this. Fantastic. Yeah, it's going to be a little shorter today. It's got a shorter hour. Important point. Now, go ahead and write this. Write this down here. So as a note, we have delta S total greater than 0 is equivalent to heat flowing from hot to cold. Hot to cold. Okay? So I'm going to formulate that as the second law of thermodynamics, and that is that the entropy of an isolated system increases. Okay. The entropy of an isolated system increases, or in the limit it stays the same, okay, but it doesn't decrease. Individually, you know, these this entropy decreased, this one increased, but taken together as an isolated system, the entropy increased. Okay, so let's write that down and we'll have made some good progress here. So let's just call this second law of thermodynamics. The entropy of an isolated system increases. Okay, but yeah, that's just a basic statement, but this is what we're supposed to think, right? Energy flow hot to cold. Okay, very general. Entropy of an isolated system increases. Yeah, what's the first law of thermodynamics? First law we've already had. The first law is conservation of energy in the most general sense. Okay. So the first law is conservation of energy. You know, we had conservation of energy earlier just with things rolling up and down a hill, that type of thing, the pendulum. But when you include thermal physics, conservation of energy is much richer because now there's work and there's thermal energy. Okay, so conservation of energy, mechanical, thermal, etc. All energy, if you add it all up, it's conserved. Okay. So the second law of thermodynamics, entropy of an isolated system increases. I'll underline that. First law, energy is conserved. So entropy increases. And once again, and not for the last time, this is identical to energy flowing from hot to cold. And this calculation showed that delta S total increased, right? It's an isolated system, increased when the energy flowed from hot to cold. Okay, good. That's what we're going to leave it with today. Okay, I don't have any recommendations for you. May want to look some of this up, but as far as the example goes, we have some good examples for this. So I wouldn't really think you need any printouts or anything. What we will do next time is start talking about heat engines, and then I'll be asking you to print out all manner of pictures. Okay, good. See you then.